Time doesn't always move the same way. Sometimes it stretches. Sometimes it pools in unexpected places, lingers where you wouldn't think to look. Tonight, we're staying in one of those places. Not a place in space, but a place in time. The instant before something becomes definite. Before probability hardens into fact. Before the world chooses. Welcome to the Sleepy Physicist. To those of you who've been here before, thank you for returning to this quiet space. To those finding this for the first time, I'm glad you're here. If this helps you rest, a like or subscribe helps others find their way here too. Let's begin. Imagine a coin. Mid-flip. Not rising, not falling yet, but suspended in that perfect arc where gravity hasn't quite claimed it. In the everyday world, we think of it as already decided. The forces are set. The spin rate, the air resistance, the exact angle of release. Classical physics would say the outcome exists already, encoded in motion too complex to track. But in the quantum world, there is no hidden answer. The coin genuinely doesn't know. It exists in both states at once, heads and tails overlapping, until something forces a choice. And somewhere between these two pictures, between the quantum blur and the classical certainty, there's a boundary, a threshold, an instant where one becomes the other. This chapter stays there. Think of it this way. A quantum particle doesn't occupy a single position. It exists as a spread of possibilities, a cloud of potential locations, each with its own likelihood. This isn't metaphor. The particle is genuinely distributed across space until something interacts with it. That interaction, that moment of contact with the larger world, collapses the cloud. The spread of possibilities reduces to one outcome, one position, one state. But how long does that take? Is it instantaneous? Does it happen over microseconds? Nanoseconds? Or is there structure to the collapse itself? Layers of transformation we can't yet see? No one knows. What we do know is this. The transition isn't about size alone. A single atom can behave quantum mechanically. So can a molecule. Under the right conditions, even clusters of thousands of atoms maintain quantum behavior. But at some point, the world intrudes. Photons scatter off the object. Air molecules collide with it. The gravitational field around it shifts, however slightly. Each interaction is a measurement. Each contact carries information away. And with enough interactions, the quantum possibilities become so entangled with the environment that tracking them becomes impossible. This process has a name. Decoherence. Not collapse, but entanglement spreading outward until the original superposition is buried. Still there, technically, but irretrievable. And it happens fast. For a dust particle in air, decoherence occurs in less than a billionth of a second. For something larger, a grain of sand, a cell, a coin, the timescale shrinks further. But there's still an instant, however brief. A span of time where the object hovers between states, neither fully quantum nor fully classical. A flicker. Can we see it? In laboratories, physicists try. They cool atoms to near absolute zero, isolate them from vibration, from light, from anything that might disturb them. They create conditions where quantum behavior persists longer than it should. And then they watch. They measure the moment a superposition begins to fade. They track how quickly entanglement spreads. They map the boundary, one experiment at a time. But even in those perfect conditions, the transition is never clean. It's not a switch, it's a gradient, a slow bleed from one regime into another, shaped by how the system couples to its surroundings. Temperature matters. A warm object radiates photons constantly, each one carrying away information about the object's state. Decoherence accelerates. Isolation matters. The fewer particles interacting with the system, the longer quantum behavior survives. This is why quantum computers must be shielded so carefully. A single stray photon can collapse a calculation. Size matters too, but not the way you'd think. It's not that large things can't be quantum. It's that large things have more surface area, more ways to interact with their environment, more channels for decoherence to flow through. So the boundary isn't a line, it's a region, a zone of transition where quantum rules fade and classical patterns emerge, not because the physics changes, but because the environment drowns out the quantum signal. And in that zone, strange things happen. There are states called Schrödinger cat states, named after the thought experiment. Macroscopic objects prepared in quantum superpositions, a tiny mirror vibrating in two directions at once, a current flowing clockwise and counterclockwise simultaneously. These states exist. They've been created, but they vanish almost immediately. The larger the system, the faster decoherence claims it. The flicker shortens. What happens during that flicker? Is the system still following quantum laws? Or has it already crossed into classical behavior, but we haven't noticed yet? Does the transition have stages? Intermediate forms? No one can say. Some physicists think the boundary is smooth. Quantum mechanics never truly ends. It just becomes so diffuse, so tangled with the environment, that it looks classical from the outside. Others think there might be something else. A threshold where quantum rules genuinely stop applying, where superposition doesn't just hide, but ceases, where collapse is real. But if that's true, what triggers it? What decides the moment? And does anything witness that moment, or does it happen in silence, unobserved even by the universe itself? The coin is still falling. In the time we've been speaking, countless quantum events have resolved around you. Electrons in the wires nearby have settled into definite states. Photons striking your retina have collapsed into specific positions. Air molecules have chosen trajectories. Each collapse took time. Not much, but some. And in that interval, however unimaginably brief, the universe hovered, uncertain. We live on the far side of that uncertainty, where things have already chosen, where the world feels solid, predictable, bound by outcomes instead of probabilities. But the flicker is always there. Behind every certainty, there was an instant where it could have gone differently. An instant where the coin was still spinning, where the answer hadn't yet formed. And though we can't see it directly, though it passes too quickly to catch, it shapes everything. The boundary between quantum and classical isn't just a feature of physics. It's the reason the world looks the way it does. It's why chairs stay chairs, why light moves in straight lines most of the time, why the past feels fixed and the future open. Decoherence makes reality stable, but it also hides the strangeness, the infinite branching possibilities that exist beneath every moment, buried so quickly we never see them flicker. Somewhere in that burial, in that instant before the world decides, there's a thickness we can't measure yet. But it's there. always. The coin lands, heads or tails, one outcome, chosen. But for a moment, just before, it was both. A single atom moves differently than a rock. This much is known. An atom can exist in multiple states simultaneously. It can pass through two gaps at once. It refuses to have a definite position until forced. A rock does none of this. It sits. It occupies one location. Its mass, its edges, its surface, all agreed upon. The question isn't why atoms behave quantum mechanically. The question is why rocks don't. Both are made of the same matter. Both follow the same fundamental laws. Yet somewhere between one atom and 10 to the 23rd atoms, quantum behavior disappears. Where does it go? Start small. One atom in isolation maintains superposition indefinitely. Two atoms bonded together can do the same, as long as nothing disturbs them. 3 atoms, 10, 100. The behavior doesn't change yet. The system still spreads across multiple states. It still interferes with itself. Quantum mechanics holds. But add more atoms and something begins to shift. Not in the physics, in the environment. Each atom interacts with the space around it. It exchanges photons with nearby surfaces. It tugs on the electromagnetic field. It responds to gravity, however faintly. These interactions carry information outward, and information is the key. When a quantum system interacts with its surroundings, the surroundings learn something about the system's state. Not through conscious observation, just through physical contact. A photon bouncing off, a molecule colliding, a field bending. Each interaction entangles the system with the environment. The quantum possibilities don't vanish. They spread. They become shared between the object and everything it touches. And with enough interactions, the original superposition becomes impossible to track. It's still there mathematically, but functionally, it's gone. This is decoherence again, not collapse, dispersal. The rate of decoherence depends on how many interaction channels exist. A single atom has few, a molecule has more, a grain of dust has billions. Each atom in the grain couples to the environment independently. Each one exchanges photons. Each one vibrates, radiates heat, responds to passing fields. Multiply those channels together, and decoherence happens faster than anything else in physics. For a dust particle at room temperature, quantum superposition lasts less than a trillionth of a second. For a bacterium, it's even shorter. So size matters, but not because large objects obey different rules. They simply have more surface area, more ways to leak information, more channels for the environment to listen through. But what if you remove the environment? In theory, a large object isolated from all interactions should maintain quantum behavior. No photons, no air molecules, no gravitational radiation, perfect silence. In practice, perfect isolation is impossible. Even in deep space, the cosmic microwave background fills everything. Photons left over from the Big Bang pass through constantly, each one capable of decoherence. Even gravity can't be shielded. Mass curves space-time. That curvature radiates outward. Information spreads. Still, physicists try. They cool systems to millikelvins. They trap ions in magnetic fields. They suspend molecules in vacuum chambers. And they've succeeded in making larger and larger objects behave quantum mechanically. A molecule with 800 atoms was put into superposition in 2019. It existed in two places at once. Not metaphorically, measurably. The superposition lasted only milliseconds. Then decoherence claimed it. But for that brief window, quantum behavior persisted in something large enough to see under a microscope. The size threshold keeps moving. So when does quantum mechanics truly end? At what point does size force classical behavior, no matter how perfect the isolation? Some think never. In this view, quantum mechanics applies to everything: atoms, molecules, dust, people, planets. The reason large objects appear classical is purely environmental. Decoherence happens so quickly that superpositions vanish before measurement. But the underlying physics never changes. A rock is quantum, just decohered. Others suspect there might be a true boundary, a mass limit where quantum mechanics genuinely stops applying, where gravity itself forces collapse, where superposition becomes physically impossible, not just hidden. The threshold would be somewhere around a microgram, a speck of dust visible to the naked eye. Anything larger would be classical by necessity. Anything smaller could remain quantum. But no experiment has confirmed this yet. The technology doesn't exist to test it. So the question remains open. Does size eventually matter absolutely? Or is it always just about isolation? Either way, something happens between single atoms and everyday objects. The mathematics changes shape. Tracking a system with one atom requires describing two possible states: spin up or spin down, position A or position B. 2 atoms require 4 states, 3 require 8, 10 require over 1,000. 100 require more states than there are particles in the universe. The complexity grows exponentially, and while the equations still work in principle, calculating them becomes impossible. Not just difficult, impossible. There isn't enough matter in the cosmos to build a computer capable of tracking the quantum state of a grain of sand. The information content exceeds physical limits. So perhaps the classical world emerges not from new physics, but from computational inaccessibility. Quantum behavior remains underneath, but the universe itself can't keep track of it. So it simplifies, averages, decoheres. Size forces approximation. But approximation to what? To the most probable outcome, the state that minimizes energy, the configuration most compatible with the environment. In most cases, that means localization. The object settles into one position, one momentum, one configuration. Not because it has to, because everything else is unstable. Quantum systems want to spread. They want to explore all possibilities. But the environment constrains them. It forces coherence by demanding consistency. The universe prefers states that don't contradict themselves across space. And the larger the system, the more constraints exist. A single atom can be 2 places at once because nothing nearby cares. A rock cannot. Because every atom in the rock is coupled to every other atom, and to the ground beneath it, and to the air around it. The web of connections is so dense that superposition would require coordinating quadrillions of particles simultaneously. And decoherence happens faster than coordination. So the rock stays put. Not because of size alone, because of connection. Isolation allows quantum behavior. Connection suppresses it. And large objects are never truly isolated. But in principle, they could be. A macroscopic object in perfect vacuum, cooled to absolute zero, shielded from all fields, could maintain superposition. For a while. Until its own gravity betrays it. Mass curves space-time. Curvature propagates outward at light speed. A superposition of positions means a superposition of gravitational fields, and those fields radiate. The object decoheres itself, just by existing. This is why some think there's a true size limit. Beyond a certain mass, gravity makes isolation impossible. The object can't hide from its own field. Quantum mechanics might still apply, but it can't be observed, can't be measured, can't persist long enough to matter. And perhaps that's where the boundary sits. Not where the rules change, but where they become unverifiable. Where quantum and classical merge, not because one replaces the other, but because no experiment can tell them apart. Size stops mattering when measurement stops working. And maybe that's enough. An electron leaves a point, travels, arrives somewhere else. But between leaving and arriving, it doesn't take a path. It takes all of them. Every possible route through space. Straight lines. Curves. Impossible detours that loop backward in time before correcting. All of them happening simultaneously. This isn't speculation. It's measurable. When you calculate where an electron will end up, you must include every path it could have taken. Add them together. Let them interfere. Some routes cancel others. What remains is the probability. The electron doesn't choose. It explores. And in that exploration, it exists in many places at once. But then something changes. Maybe the electron passes near a charged plate. Maybe a photon scatters off it. Maybe nothing visible happens at all. Just the background hum of the electromagnetic field shifting slightly. And one of the locations fades. Not instantly. Not violently. Just less. The electron still occupies both positions mathematically, but one becomes less probable, less coherent with the environment. The world begins to favour the other. It's like forgetting. The way a memory loses detail over time. You remember being somewhere, but the edges blur. The colour drains. Eventually only the outline remains. Then, not even that. The electron forgets it was ever in two places. Or rather, the universe forgets. Because the electron doesn't hold the memory alone. Every interaction spreads the information outward, into photons, into nearby fields, into the fabric of space-time itself. And once spread, it can't be gathered back. This is entanglement, not the kind that links distant particles, the kind that links objects to their surroundings, where every quantum state becomes correlated with the environment, where isolation ends. The electron's superposition doesn't collapse. It dilutes, spreads so thin across so many other systems that recovering it would require knowing the exact state of everything it touched. Every photon, every vibration, every fluctuation in the vacuum. Impossible. So the second location fades, and the first remains. But why that one? Why not the other? What decides which location the universe keeps? No one knows. In standard quantum mechanics, the choice is random, weighted by probability, but fundamentally unpredictable. The electron has a 60% chance of being here, 40% there. Roll the dice. But dice need someone to roll them. And there's no hand here. Just mathematics. Just wavefunction evolution. Just the slow leaking of coherence into the environment. And yet, one outcome happens. The forgetting completes. Some interpretations say both locations persist. The universe splits. One branch contains an electron here, another contains it there. You only experience one branch, so it feels like a choice was made. But both exist. In this view, nothing is forgotten. The electron remembers both locations. You just can't access the other memory anymore. It's in a different world now. Does that help? Does it matter whether the second location vanished or just became unreachable? Maybe not. Either way, from inside one branch, the effect is the same. One outcome, one location. The object forgot itself. Or you forgot half of it. There's another possibility. That the forgetting isn't about randomness or splitting at all. That it's about compatibility. The environment has a state, temperature, electromagnetic noise, gravitational curvature, all the background conditions of space. A quantum superposition must remain consistent with that background. If one location in the superposition creates a field that contradicts the environment, that location becomes less stable. It decoheres faster. The environment erases it. Not through measurement, through incompatibility. Like a wrong note in a chord. It doesn't get chosen away. It just can't sustain itself against the harmony. In this picture, the universe doesn't decide. It filters. And what remains is whatever fits. The electron ends up where it can coexist with everything around it. Not because something chose that spot, because the other spot couldn't hold. But then what is the electron doing before it settles? Existing. In both places. As a field. A distributed possibility. Not located anywhere specifically. Not travelling between points. Just present. Spread. And then the spreading stops. Distance affects this. The farther apart the two locations are, the more different their environments become. Different temperatures. Different field strengths. Different curvatures. Each location entangles with its own local surroundings, and those surroundings don't talk to each other, so the coherence between the two locations weakens. The electron forgets faster when its two selves are far apart. Time matters too. A superposition held for 1 nanosecond might survive. Held for 1 millisecond, decoherence creeps in. Held for 1 second, it's gone. The environment has learned too much. Every moment that passes, more information leaks. More entanglement forms. The memory of both locations spreads thinner, until one fades completely. But here's the strange part. The fading isn't symmetrical. One location usually fades faster than the other. Not because it's less probable, because it's less stable, less aligned with the environment. So in a sense, the environment does choose. Not consciously, just structurally, by being what it is. A warm environment favours localized states, high-energy states, states that radiate quickly. A cold environment allows delocalization, lets superposition linger, permits the object to spread. So could you stop the forgetting entirely? Freeze the object in superposition forever? Almost. At absolute zero, thermal decoherence stops. No photons radiate. No vibrations disturb the system. Quantum coherence can persist indefinitely. But absolute zero is unreachable. And even if you got close, other sources of decoherence remain. Gravity, cosmic rays, virtual particles flickering in the vacuum. The universe is never truly still, so the forgetting always continues, just slower. There are systems where forgetting takes years. Superconducting loops, currents flowing in two directions simultaneously, shielded from the environment so carefully that decoherence barely touches them. But eventually, even they settle. The superposition fades. One direction remains. And when it does, no trace of the other direction survives. No record. No echo. Just absence. The object forgot. And the universe forgot with it. This happens constantly. All around. Electrons settling into atoms. Photons choosing paths. Molecules deciding configurations. Each one a small forgetting. Each one erasing a possibility that once existed. And we don't notice, because by the time we could measure it, the forgetting is already complete. The object has already chosen, or been chosen for, or simply stopped remembering what it was. The mathematics still contains both locations. Technically, in the full quantum state of the universe, every possibility that ever existed still exists, buried in correlations, hidden in entanglement. But from here, from inside, we only see one, and the other fades, like a thought half remembered, like a place you've been but can't quite locate anymore. The electron was there, and here, and now it's only here, not because it moved, because everywhere else became impossible, incompatible, forgotten, and the world closed around the one location that remained, as if the other never was. You can feel temperature in your hands right now, the warmth of your skin radiating outward into cooler air, energy dispersing molecule by molecule into the space around you. And this movement, this constant thermal motion, is what pulls quantum systems back into the classical world. Heat is movement at the smallest scale, atoms vibrating in their bonds, electrons jumping between energy levels, photons streaming outward from any surface warmer than absolute zero. And each of these motions carries information about the system's state, scattering it into the environment where it can never be fully recovered. But remove the heat, let temperature fall toward the lowest possible value, and something changes in how matter behaves, not in the fundamental laws, but in what those laws allow to persist. At room temperature, thermal energy dominates. Particles move fast enough that quantum effects blur into statistical averages, individual uncertainties washed out by the chaos of constant collisions. So you see only the aggregate behavior, solid objects with definite positions, gases with measurable pressure, liquids that flow predictably from one container into another. Everything stable, everything decided. But cool an object down, reduce the thermal jitter, slow the vibrations until they approach their minimum possible amplitude, and quantum behavior begins to surface. Not because new physics appears, but because the noise that was drowning it out finally quiets. At a few degrees above absolute zero, atoms in a gas stop bouncing off each other with random violence and instead begin to move in coordinated waves, their quantum nature no longer hidden beneath thermal chaos, but exposed, visible, even macroscopic. They form what's called a Bose-Einstein condensate, thousands or millions of atoms occupying the same quantum state simultaneously, behaving not as individual particles, but as a single coherent entity, a droplet of matter where the usual separation between one atom and another dissolves because the temperature is too low to maintain it. This isn't a metaphor, it's a literal merging of quantum identities. The atoms spread across the same region of space without distinct boundaries, their wave functions overlapping so completely that asking which atom is which becomes meaningless. And this only happens because heat, the thing that normally forces particles into separate localized states, has been removed almost entirely. Temperature measures the average kinetic energy of particles, how fast they're moving, how much they're vibrating, and that motion translates directly into how quickly quantum coherence decays, because every collision, every thermal photon emitted or absorbed, entangles the system with its environment just a little bit more. Warm objects radiate constantly, infrared photons streaming outward in all directions, each one carrying away a tiny piece of information about the object's internal state. And if that object were in a quantum superposition, each emitted photon would become entangled with the superposition, branching the environment into states that correspond to different outcomes, until the original coherence is buried beneath layers of correlation too complex to untangle. So warmth destroys superposition, not through some special interaction, but simply through volume, the sheer number of decoherence events happening per second, overwhelming any attempt to keep quantum states isolated. But in the cold, that volume drops. Thermal radiation slows. Phonons, the quantized vibrations of matter, freeze into their lowest energy modes, and the rate at which information leaks into the environment decreases exponentially with every degree you remove. At a few millikelvins, a few thousandths of a degree above absolute zero, you can trap individual ions in electromagnetic fields and watch them hover in superpositions of position for seconds, minutes, even hours. Their quantum uncertainty preserved because the environment is too cold to interrogate them, too still to force a decision. The ion exists here and also a micrometer away, both locations real, both contributing to its wave function, and the only reason this persists is that nothing warm enough to decohere it is nearby. No thermal photons, no vibrating surfaces, just the controlled emptiness of an ultra-high vacuum chamber chilled to near absolute stillness. And you can measure this, not by collapsing the superposition, but by letting the two locations interfere with each other, applying forces that depend on position, and watching how the ion responds, seeing patterns that only make sense if both locations existed simultaneously. Proof written in motion that uncertainty held. This is why quantum computers need to be cold. Not just cold, but colder than outer space. Colder than any naturally occurring environment in the universe. Because the qubits they use, the quantum bits that hold information in superposition, must remain coherent long enough to perform calculations. And even a single stray thermal photon can collapse the computation into nonsense. At 15 millikelvins, the temperature of many quantum processors, thermal energy is so low that superconductivity emerges, electrons pairing together and flowing without resistance, their collective motion forming a macroscopic quantum state that can be in two current directions simultaneously, clockwise and counterclockwise at once, a superposition of flows large enough to drive measurable magnetic fields. And this state, this macroscopic quantum coherence, only exists because the environment is cold enough that decoherence takes seconds instead of nanoseconds, giving you time to manipulate the system, to encode information in its quantum structure, to perform operations that would be impossible if warmth were present. But even at these temperatures, Decoherence doesn't stop entirely. It only slows, because perfect isolation is impossible, and even the coldest systems are still embedded in a universe that refuses to be completely still. Cosmic rays pass through the apparatus, high-energy particles from distant supernovae colliding with the shielding and occasionally penetrating deep enough to disturb a qubit, collapsing its state unpredictably. Vibrations from the building, from traffic outside, from seismic tremors too faint to feel, propagate through the mounting structure and shake the system just enough to couple it to the environment. And even the vacuum itself fluctuates, virtual particles appearing and disappearing in accordance with quantum field theory, their brief existence enough to entangle with the system and carry information away. So cold gives you time, extends the window in which quantum behavior can be observed and controlled, but it doesn't grant permanence. The universe still presses in, still demands that coherence eventually fade, just more slowly, more gently. And this raises a question that feels almost philosophical, but is actually physical. Whether cold is permission for quantum states to exist, or whether it's a prison that traps them in uncertainty, preventing the collapse that would otherwise occur naturally. Because in the warm world, particles settle. They choose positions and momenta and configurations. They become definite through interaction with their surroundings. And while that definiteness means the loss of superposition, it also means stability, predictability, the ability to persist in a single state without constant external control. But in the cold, nothing settles fully. Particles hover in their ground states, the lowest energy configuration possible, but still not entirely motionless, still retaining what's called zero-point energy, the minimum quantum jitter that Heisenberg's uncertainty principle demands. And this jitter never goes away, no matter how cold you make the system. Even at absolute zero, which again is unreachable but imaginable, particles would not be at rest. They would oscillate with the smallest possible amplitude, their position and momentum still uncertain, still spread across a range of values, because quantum mechanics forbids perfect stillness, forbids the kind of complete localization that classical physics would allow. And so, cold, taken to its limit, doesn't eliminate uncertainty, it preserves it, keeps particles in their most quantum state, the state where they are least like classical objects and most like waves, like fields, like distributed possibilities that refuse to collapse into single points. You might think of it like this. Warmth is the world's way of asking questions. Each thermal interaction a probe that demands an answer. And cold is the absence of questioning, the space where systems can remain ambiguous because nothing is forcing them to resolve. And in that space, strange things become possible. Not just superpositions of single particles, but collective quantum states involving thousands or millions of atoms. Behaviors that have no classical analogue. Superfluidity, where liquids flow without friction. Superconductivity, where currents persist indefinitely. Quantum entanglement between macroscopic objects separated by measurable distances. All of these emerge when temperature drops low enough that thermal decoherence stops overwhelming quantum coherence, when the environment becomes quiet enough that the subtle correlations between particles can organize into macroscopic patterns, and the system as a whole begins to behave according to rules that seem impossible from a classical perspective. But bring the warmth back. Let the temperature rise even slightly, and the fragile quantum structure dissolves. Particles decouple from their collective state. Superfluids start to experience friction again. Superconductors develop resistance. Entanglement breaks down into statistical independence. Everything returning to the classical behaviors we expect from ordinary matter. Not because quantum mechanics stops applying, but because the environment reasserts itself, begins asking questions again, measuring the system, whether anything conscious is watching or not. And those measurements, Those unavoidable interactions with surrounding thermal noise force the quantum possibilities to collapse into definite outcomes. And so, temperature isn't just a number, it's a threshold, a parameter that determines whether the quantum world stays hidden or becomes visible, whether uncertainty remains or resolves, whether particles behave like waves or like points. And the threshold is low, astonishingly low, far below anything you'll encounter naturally, which is why quantum mechanics feels distant from everyday experience, why it seems like a separate realm of physics that only applies to carefully controlled laboratory conditions. But it's not separate, it's just buried, hidden beneath the warmth that surrounds us, the constant thermal motion that keeps everything classical, keeps particles decided, keeps the world solid and predictable. Remove that warmth, and the quantum world surfaces, not as something new, but as something that was always there, waiting underneath, held in check by nothing more than heat. And in the deepest cold we can create, it emerges fully. Particles spreading across space, refusing positions, existing in multiple states simultaneously, the way they always do when nothing forces them to choose. Cold doesn't create quantum behavior, it allows it. Warmth doesn't destroy it, it covers it. And the difference between the two is just energy, just motion, just the speed at which atoms vibrate. Nothing more. Light passes through a barrier. Two narrow slits cut into an otherwise solid surface. On the far side, a screen waits to record where the light arrives. If light behaved like particles, you'd expect two bright bands, one behind each slit. Simple geometry. That's not what happens. Instead, the screen shows multiple bands. Bright, dark, bright again. A pattern of alternating intensity spreading across the detection area. This is interference, the signature of waves. When two waves meet, they can add together or cancel out, depending on whether their peaks align or oppose. Constructive interference creates brightness. Destructive interference creates darkness. So light must be a wave, spreading through both slits simultaneously, overlapping on the far side, interfering with itself. Except light also comes in discrete packets, photons, individual quanta that can be detected one at a time. Send photons through one by one, wait seconds between each emission. Let each photon cross the apparatus alone, with no other photons present. The interference pattern still appears. Not immediately. Each photon arrives at a single point on the screen. One dot. Random location. No pattern visible yet. But send 1,000 photons. 10,000. The dots accumulate. And slowly, the pattern emerges. Bands of high density where constructive interference occurs. Gaps where destructive interference suppresses arrivals. Each individual photon interfered with something, but not with other photons. There were no other photons. It interfered with itself. The photon passed through both slits, not sequentially, simultaneously. Its wave functions spread across both openings, travelled both paths, and recombined on the far side where the two routes converged. This has been verified with electrons, with atoms, with molecules containing hundreds of atoms. The pattern persists. Interference happens regardless of what you send through the slits, but only if both paths remain possible. Place a detector at one slit, something that registers which opening the particle uses. A device that answers the question, left or right. The interference pattern vanishes. Not because the detector blocks the path. It doesn't. The particle still passes through, still reaches the screen. But now it arrives in one of two bands. Left slit or right slit. No interference. No alternating bright and dark regions. Just two separate distributions corresponding to the two possible paths. The detector didn't physically obstruct anything. It just measured. It acquired information about which path the particle took. And that information, that knowledge existing anywhere in the system, prevents interference. The two paths no longer cooperate. Why? What carries the connection between paths that never physically touch? What mechanism allows one route to know about the other? Nothing travels between them. No signal. No hidden communication. The paths are separated by space, by the solid barrier between the slits, by distances that could in principle be meters or kilometers. Yet they interfere. The mathematical description is straightforward. The particle's wave function splits at the barrier. Part of it passes through the left slit, part through the right. These two portions propagate independently toward the screen. When they arrive, they overlap, add together. The amplitude of the combined wave function determines where the particle is likely to be detected. Where the two portions arrive in phase, peaks aligned, the combined amplitude is large. High probability. Bright band. Where they arrive out of phase. Peak, meeting, trough. They cancel. Zero amplitude. No detections. Dark band. The interference happens in the wave function itself, not in physical space. The particle doesn't take both paths as separate journeys. It exists as a distributed field that encompasses both routes simultaneously. And that field has structure, phase, a property that varies continuously across space and determines how different portions combine when they meet. This phase is sensitive to everything along the path. Distance travelled, electromagnetic fields encountered, gravitational potential, even the geometry of space-time. A photon travelling through curved space accumulates phase differently than one travelling through flat space. The curvature imprints itself on the wave function. And when two paths with different curvatures interfere, the pattern shifts. This has been measured. Neutron interferometers placed at different heights in Earth's gravitational field show phase shifts consistent with general relativity. The neutrons travelling the upper path experience slightly less gravitational time dilation. Their phase evolves differently. The interference pattern rotates. So the two paths know about each other through phase, through a property of the wave function that remains coherent across both routes. As long as nothing measures which path was taken, measurement destroys this coherence, not by disturbing the particle, by entangling the environment with the path information. A photon scatters off the particle as it passes through the left slit. That photon now carries information correlating it with the left path. The environment has branched. In one branch, the photon scattered and the particle went left. In another, no scattering occurred and the particle went right. These branches no longer interfere. They've become orthogonal, separate histories. The particles still pass through both slits in some sense, but the coherence between the two paths has been lost, diluted into the environment. And without coherence, there's no interference. Can you restore it? Sometimes. If the information about which path was taken remains accessible, concentrated in a single system that can be controlled, you can erase it. Make the detector forget. Return the system to a state where both paths are equally possible again. And when you do, interference returns. This is called quantum erasure. The pattern on the screen depends not on whether a measurement happened, but on whether the information from that measurement still exists anywhere. Erase the information, and the particle behaves as if both paths were taken. Preserve the information, and it behaves as if only one path was real. The past changes based on what you do with the record. Not causally. The particle already arrived at the screen, already left its mark. But which pattern that mark belongs to, interference or no interference, depends on decisions made after detection. This isn't time travel. Information doesn't flow backward. It's that the particle's behavior was always conditional on the full experimental setup, including what would later happen to the path information. The two paths remain connected across time as well as space. Interference has been demonstrated with paths separated by kilometers. Photons traveling through optical fibers over vast distances. One path routed through a laboratory, another sent across a city. Both converging at a detector where interference fringes appear. The photons didn't know the route lengths when they started. The fiber could have been coiled differently. Buildings could have been in the way. None of that information was available at the source. Yet the interference pattern reflects the exact path difference. Every centimetre of extra fibre shifts the fringes. Every environmental vibration that changes the optical length modulates the visibility. The paths talk to each other without communication. Or rather, they don't need to talk. They're not separate. The particle isn't on one path or the other. It's in a state that includes both. A superposition that spans the entire apparatus. And superpositions aren't located in one place. They're properties of the wave function as a whole. Distributed. Non-local. This non-locality isn't the same as entanglement between separate particles. It's simpler. A single particle whose quantum state extends across multiple regions of space. Regions that remain phase coherent. But phase coherence is fragile. Any interaction that distinguishes the paths, that leaves a trace of which one was taken, breaks it. A scattered photon. A vibrating mirror. A thermal fluctuation in the fiber. And in everyday environments, such interactions are constant. Air molecules collide with macroscopic objects billions of times per second. Each collision entangles the object's position with the molecule's trajectory. Path information scatters into the environment faster than it can be controlled. So interference vanishes at large scales. Not because particles stop being quantum, because coherence between different paths decays before measurement. You could in principle send a baseball through two widely separated hoops and see interference, if you could isolate it completely. Remove all air. Shield it from thermal radiation. Prevent gravitational decoherence. Measure its arrival without disturbing the paths. None of this is practically possible, but the physics doesn't forbid it. The baseball would interfere with itself. Its wave function would pass through both hoops. The pattern would appear. Quantum mechanics applies to everything. Interference is universal. The question is only whether coherence survives long enough to observe it. And for most objects, in most situations, it doesn't. The environment measures too quickly. Path information leaks before interference can manifest. But the principle remains. Two paths that never touch still affect each other. Not through forces, not through signals, through coherence, through the unity of the wave function that describes both. And that unity persists until something breaks it, until knowledge enters, until the universe learns which path was real. And then the paths separate. The pattern fades. Interference ends. Not because the physics changed, because the information escaped. The word measurement suggests intention. Someone performing an action. A scientist with equipment. Eyes watching. attention-focused. But in quantum mechanics, measurement means something different, simpler, more physical. It means any interaction that creates a record. A particle scatters off another particle. Their trajectories change. Information about the first particle's momentum transfers to the second. That's measurement. No observer required. No consciousness. Just physics. A photon traveling through space encounters an atom. The photon's wavelength determines whether it gets absorbed. If absorbed, the atom jumps to a higher energy state. The atom now carries information about the photon's frequency. The photon has been measured by the atom. Even if no one looks at the atom afterward. Even if the atom sits in darkness for 1 billion years. The measurement occurred. The interaction happened. Information transferred. This is what collapses superposition. Not observation in the human sense. Interaction in the physical sense. Before measurement, a particle exists in multiple states. Spin up and spin down. Here and there. Moving fast and moving slow. All simultaneously. The measurement couples the particle to something else. The measuring device. The environment. Another degree of freedom that can record the outcome. And once coupled, the superposition spreads. It's no longer confined to the particle alone. Now the particle plus environment system is in superposition. One branch where the particle is spin up and the detector reads up. Another branch where it's spin down and the detector reads down. From inside either branch, the particle appears to have a definite state. The superposition hasn't disappeared. It's been shared. This is decoherence again. The environment becomes entangled with the quantum system. And because the environment is large, complex, uncontrollable, the different branches stop interfering with each other. They become effectively separate. The particle has been measured, even though no person was involved. Consider a grain of dust floating in air. Air molecules strike it constantly, thousands per second. Each collision transfers momentum. Each one creates a correlation between the dust grain's position and the molecule's trajectory. Every molecule that bounces off the grain carries away information about where the grain was when contact occurred. That information disperses into the surrounding air, spreads across billions of other molecules through subsequent collisions, becomes irretrievable. The dust grain's position has been measured, continuously, by the air. This is why the grain doesn't exhibit quantum behavior. Not because it's too large, because it's too measured, too coupled to its environment, too exposed. In vacuum, isolated from air, the grain could maintain superposition longer, still not indefinitely. Thermal photons would still interact with it, the cosmic microwave background, stray electromagnetic fields. But the timescale would extend, microseconds instead of nanoseconds, maybe milliseconds under perfect conditions. The less the environment measures, the longer quantum states persist. Scientists building quantum computers understand this deeply. They don't just cool their systems to reduce thermal noise. They shield them from light, from magnetic fields, from vibrations, from cosmic rays. Every photon that enters the apparatus is a potential measurement. Every fluctuating field, every mechanical vibration that couples to the qubits. The goal is to delay measurement as long as possible, to create a space where quantum superpositions can exist without the environment learning about them. But perfect isolation is impossible. The shielding itself has temperature, emits photons. The vacuum chamber has walls. The walls radiate. Even in the best laboratories, the environment whispers constantly. And those whispers accumulate. Information leaks. Measurements happen whether intended or not. What does the environment do with this information? Nothing. It doesn't process it, doesn't store it in any organized way. The information just disperses, becomes encoded in the microscopic states of countless particles, in thermal fluctuations, in electromagnetic noise. Recovering that information would require knowing the exact quantum state of every particle in the environment, every atom in the air, every photon that's scattered, every vibrational mode of every molecule. This is thermodynamically impossible. The entropy is too high. The information is too diluted. So for all practical purposes, it's gone. But theoretically, in the full quantum description of the universe, the information still exists. Buried in correlations, hidden in entanglement, irretrievable but not destroyed. This raises a strange question. If the information can't be accessed, does the measurement count? Has the superposition truly collapsed if the record is unreadable? Different interpretations answer differently. In the Copenhagen interpretation, measurement causes genuine collapse. The superposition ends. One outcome becomes real. The others cease to exist. And this happens as soon as information transfers to the environment, accessible or not. In the Many-Worlds interpretation, no collapse occurs. The universe branches. Every measurement creates new branches, one for each possible outcome. All branches exist. We experience one. The others are inaccessible, not non-existent. In decoherence-based interpretations, collapse is an illusion. The superposition remains, but becomes so entangled with the environment that tracking it requires impossible precision. Effectively, it looks collapsed. Functionally, it behaves collapsed, but fundamentally, it's still there. All three agree on the observables, on what experiments will measure. They differ only in what they say about the parts we can't see. But they all agree on this. Measurement doesn't require awareness. A rock can measure a particle. A photon can measure another photon. Empty space can measure through its quantum fields. Consciousness plays no special role. This was once debated. Early quantum theory struggled with what counted as measurement. Some proposed that conscious observation was required to collapse the wave function, that until a mind perceived the result, superposition persisted. This view has been abandoned. Experiments show decoherence occurring in systems where no consciousness is present. Particles in deep space, atoms in sealed chambers, photons travelling through fibre optics with no observer at either end. Measurement happens automatically, continuously, whenever sufficient interaction occurs. And sufficient is vague by necessity. There's no sharp threshold, no exact number of entangled particles that defines when collapse happens. It's gradual, progressive, a slow transition from coherent superposition to classical mixture. Weak measurements exist, interactions that extract only partial information. They disturb the system less than full measurements, collapse the wave function only partially. You can measure a particle's position roughly without destroying its momentum uncertainty entirely, or measure its energy weakly without fully collapsing its state. The disturbance scales with how much information you extract. More information means stronger coupling to the environment. Stronger coupling means faster decoherence. So measurement is a spectrum, not binary, a continuum from no interaction to complete entanglement. But once information leaves the system, even weakly, recovery becomes difficult. Quantum error correction tries to address this. By encoding information redundantly across multiple qubits, errors introduced by environmental measurement can be detected and reversed. Up to a point. But correction requires measurement too. Special measurements designed to reveal errors without revealing the encoded information. Syndrome measurements that collapse only certain combinations of qubits. It's delicate. Every correction cycle introduces new opportunities for decoherence. The challenge is to correct faster than errors accumulate. And errors accumulate because the environment never stops measuring. Silence has weight. Even a perfect vacuum isn't empty. Quantum fields fluctuate. Virtual particles appear and disappear. These fluctuations interact with real particles, shift their energy levels slightly. The Lamb shift in hydrogen. The Casimir effect between conducting plates. These interactions are measurements, weak, subtle, but real. So even in perfect isolation, the quantum vacuum measures. Space itself takes note, not through intention, through structure, through the unavoidable presence of fields. To exist is to be measured, not observed, not watched, but coupled, entangled, known in the physical sense. And once known, coherence fades. Superposition spreads into the environment. The particle settles into a definite state, or appears to, depending on what you think happens beneath the surface, beneath what can be measured. But the surface is all we access. All experiments probe, all predictions concern. And on that surface, the rule is simple. Interaction creates correlation. Correlation distributes information. Distributed information looks like collapse. No eyes required. Just contact. Just the universe touching itself. Taking note. Constantly. Everywhere. A particle reaches a fork. In classical physics, it takes one path or the other, determined by forces and initial conditions. The trajectory already written into the state of the system, even if too complex to predict. The choice was made long before the fork appeared. In quantum mechanics, the particle takes both. Not as a metaphor, not as uncertainty about which path it really took. Both paths exist in the wave function with definite amplitudes, both contributing to where the particle might later be found, both equally real in the mathematical description, until something forces the system to resolve. And when that resolution happens, one outcome appears. The question is what happens to the other? Does it vanish? Retract into non-existence? Or does it continue, unobserved, in a version of reality you can no longer access? Hugh Everett proposed an answer in 1957, not as philosophy, but as a way to take the mathematics of quantum mechanics seriously, without adding extra assumptions about collapse. If the wave function describes everything, if it evolves smoothly according to Schrödinger's equation without interruption, then superpositions never truly end, they just branch. The universe splits. Every quantum event with multiple possible outcomes creates multiple worlds. One world for each outcome. All existing. All equally real. You experience one branch because your consciousness, your neurons, your physical body, exists in that branch and cannot access the others. But in another branch, another version of you experiences the other outcome. Both versions are you. Both think they're the only one. This is the many-worlds interpretation. Not many-worlds theory. It makes no new predictions, changes no experimental results, adds no testable hypotheses beyond standard quantum mechanics. It's just an interpretation, a way of understanding what the equations might mean. But it's precise, and it removes the need for collapse. No special measurement process, no observer-dependent physics, no moment when possibilities reduce to one outcome. The wave function evolves continuously, deterministically, splitting into branches that never recombine. Think of it like a river approaching an island, the current dividing around both sides, each stream continuing downstream as if the other didn't exist, even though both are part of the same river system. The water doesn't choose one channel. It flows through both. Except the branches in quantum mechanics don't rejoin. Once a measurement occurs, once the environment becomes entangled with the quantum system, the different outcomes decohere from each other. They become orthogonal in the quantum state space, meaning their amplitudes no longer interfere, no longer contribute to the same probabilities. They're separate worlds. And this happens constantly. Every photon absorbed by a molecule in your eye branches the universe into versions where different photons were absorbed, where your retina sent slightly different signals to your brain, where your thoughts diverged in ways too small to notice consciously. Every radioactive decay, every electron choosing a trajectory, every quantum event anywhere in the cosmos. Splitting. The number of branches grows exponentially, unimaginably fast. But they don't take up space. The branches aren't spatially separated, aren't located in different regions of physical space or different dimensions. They're different components of the universal wave function, different terms in the quantum state that describes everything. They coexist in the same space without interacting, because they're orthogonal, because the mathematical structure of quantum mechanics keeps them from influencing each other once decoherence sets in. It's not like parallel universes in science fiction. No barriers between them. No way to cross over. Just separation in state space. Does this mean determinism returns? In a sense, the wave function evolves deterministically according to the Schrödinger equation without any randomness or collapse. Given the state of the universe at one time, the state at any future time is completely determined. No probabilities. No uncertainty. But within any single branch, the future appears random because you can't predict which branch you'll experience. Before a quantum event, your current self will split into multiple future selves, each experiencing a different outcome. The equations tell you the amplitude of each branch, which determines how many copies of you end up in each, but they don't tell you which copy you'll be. So from the inside, it still feels probabilistic. Born's rule, the connection between wave function amplitude and probability, emerges naturally in this picture. The squared amplitude of a branch determines the measure of that branch, roughly how much of you ends up there. High amplitude means many copies. Low amplitude means few. If a quantum event has a 90% chance of outcome A and 10% chance of outcome B, the universe splits into branches where 90% of the measure goes to A and 10% to B. You're more likely to find yourself in an A branch simply because more of you exists there. But some version of you always experiences B. Always. This leads to strange conclusions about what happens over time, about rare events accumulating across branches. In some branch, every low probability event eventually occurs. Radioactive atoms that should decay in microseconds persist for years in some world. Particles tunnel through barriers they should never cross. Improbable configurations assemble themselves. These branches have very low measure. Almost none of you exists there. But almost none is not zero. Somewhere, you made every possible choice. Every decision point in your life where quantum randomness played even a tiny role, a neuron firing, a photon absorbed, a thermal fluctuation in a synapse, created branches. In some branches you turned left, in others, right. In some, your thoughts drifted one direction. In others, they went elsewhere. Most of these differences are tiny, inconsequential. Your actions remain similar across nearby branches. But integrated over years, the differences accumulate. And in low-measure branches, your life diverged radically from anything you'd recognize. This doesn't mean all possibilities occur, only quantum possibilities. Branches where the laws of physics are violated don't exist, because the wave function doesn't include them. You won't find a branch where gravity suddenly reversed, or electrons started repelling each other. The branching respects physical law. But within those constraints, everything that can happen does happen. Somewhere. The universe contains all histories compatible with quantum mechanics. Can branches ever merge? Theoretically, yes, if the different branches return to identical states. If two paths through state space reconverge perfectly, they can interfere again. This is what happens in quantum erasure experiments. But for macroscopic systems, for anything involving more than a handful of particles, reconvergence is effectively impossible. Too many degrees of freedom. Too much environmental entanglement. The branches diverge irreversibly. Decoherence is a one-way process. So the splitting is permanent, at least on timescales relevant to anything we could measure or experience. Some have objected that this picture is extravagant, that postulating countless unobservable branches violates principles of parsimony, that science should prefer simpler explanations. But Everett's response was that Many-Worlds is actually simpler than alternatives because it doesn't add anything to quantum mechanics. It just takes the equations literally. Collapse theories add a new process, a measurement postulate, an extra rule about when and how wave functions reduce. Many-Worlds uses only the Schrödinger equation, simpler mathematics, more complex ontology. Whether that trade is worth making depends on what you value in a physical theory. Critics also point out that Many-Worlds doesn't fully solve the measurement problem because it doesn't explain why we experience definite outcomes at all. Yes, the universe contains all branches, but within each branch, observers still perceive one result, one position for the particle, one reading on the detector. Why does consciousness follow individual branches instead of experiencing the superposition directly? The interpretation doesn't answer this. It assumes that macroscopic objects like brains decohere into separate branches, and that subjective experience follows one branch, but it doesn't derive this from deeper principles. It's still assumed. Yet the picture has appeal for its starkness, for the way it refuses to privilege observation or consciousness, for treating measurement as just another physical process that happens to create branching. No collapse. No randomness in the fundamental dynamics, just the relentless splitting of reality into more and more branches as quantum events accumulate. And if it's true, the splitting is happening now, with every quantum event in your body, in the air around you, in the devices nearby, in the distant stars. The universe fractures continuously into versions that differ by the outcome of a single quantum measurement, each version spawning further branches as more measurements occur, an infinite tree of worlds growing from every moment into an uncountable multitude of futures. You can't see it, can't feel it, can't detect the branching, because you're inside one branch, and the others are exactly as real as yours, but unreachable. Every version of you thinks they're in the only real world. Every version is right, and every version is unaware of the others. Unless you accept the mathematics, unless you take the wave function seriously, then they're all there, always have been. Splitting, silently, forever. You're sitting in what feels like empty space. Air, maybe. Darkness. Silence. But emptiness is never truly empty. Even in a perfect vacuum, even in a region of space scrubbed clean of every particle, every photon, every trace of matter, something remains. Fields. Quantum fields that fill all of space, that never switch off, that fluctuate even when nothing observable is happening. And these fluctuations have energy. Not much, not the kind you can harvest or use, but enough to have measurable effects. Enough to let particles borrow from nothing and pay it back before the universe notices. This is vacuum energy. 0-point energy. The minimum energy state of quantum fields, which is not zero despite the name, because Heisenberg's uncertainty principle forbids absolute stillness. A field cannot have precisely zero amplitude and precisely zero rate of change simultaneously, so it fluctuates. And in those fluctuations, particle-antiparticle pairs appear. An electron and a positron, a quark and an antiquark, a photon splitting into two photons briefly before recombining. These are virtual particles, not the same as real particles because they exist only for fleeting intervals, but they're not fictional, they have measurable consequences. They borrow energy from the vacuum, from nothing. But the loan must be repaid, and the repayment window is determined by the size of the loan. There's a relationship between energy and time in quantum mechanics, encoded in the uncertainty principle. The more energy a particle borrows, the shorter the duration it can exist. Borrow a little, and you can linger for a relatively long interval. Borrow a lot, and you must vanish almost immediately. The product of energy uncertainty and time uncertainty must exceed a fundamental constant, Planck's constant divided by 2. This isn't negotiable. It's woven into the structure of quantum mechanics. So a particle borrowing barely any energy can persist for microseconds, maybe longer. A particle borrowing enormous energy exists for only a tiny fraction of a second before annihilating with its antiparticle and returning the energy to the vacuum. The debt gets paid. Always. You might imagine this as the vacuum offering credit with strict terms. Borrow what you need, but the interest rate is extreme. Time collapses as the loan increases. And default is impossible, because the physics won't allow the particle to persist beyond its allotted span. The universe balances its books. These virtual particles aren't directly observable because they vanish before interacting with detectors in ways we can measure. But their effects appear in precision measurements of atomic energy levels, in the slight shifts caused by virtual photons surrounding an electron, in the way the vacuum polarizes near a charged particle, screening its electric field. The Lamb shift in hydrogen, the anomalous magnetic moment of the electron, both explained by virtual particles. So the borrowing is real, even if the borrowed particles are transient. But where does the energy come from? Nowhere, technically. Energy isn't created. The vacuum state has fluctuations built into it, variations in field strength that occur naturally due to quantum uncertainty. And when a particle-antiparticle pair appears, energy temporarily localizes in a way that looks like creation. But the total energy of the system, including the vacuum, remains constant. The positive energy of the particles is balanced by a deficit elsewhere, usually in the field configuration itself. Think of it as redistribution, not generation. When the particles annihilate, the energy returns to the diffuse state it started in. The vacuum relaxes back to its baseline. The fluctuation subsides. Nothing was gained or lost. But during the brief interval when the particles existed, consequences occurred. Photons scattered. Fields shifted. Interactions happened that wouldn't have happened if the vacuum were truly inert, and this happens everywhere. Constantly. In the space between your fingers right now, particle pairs are flickering into and out of existence. electrons, quarks, photons, all borrowing energy for infinitesimal durations and then vanishing. The density of these fluctuations is staggering. At any given moment, countless virtual particles populate the vacuum, their combined effects creating what we perceive as the properties of empty space, its permittivity, its permeability, the speed at which light travels through it. These aren't fixed constants of nature, but emergent properties arising from quantum activity in the vacuum. So emptiness has structure, texture, a kind of restless background hum that never ceases, and occasionally, under the right conditions, virtual particles can become real. Near the event horizon of a black hole, one particle from a virtual pair can fall inward, while the other escapes. The escaping particle becomes real because it's no longer required to annihilate. Its partner is gone, swallowed by the black hole. The black hole's mass decreases slightly to provide the energy that makes the escaped particle real. This is Hawking radiation. The vacuum borrowing energy, and through a peculiar geometric accident involving extreme gravity, managing to keep part of the loan. The black hole pays the debt instead. But in ordinary space, away from black holes, the borrowing always gets repaid on schedule. The smaller the energy borrowed, the longer the particle can exist. A virtual photon carrying very little energy, just a tiny quantum of electromagnetic field, can persist for a relatively extended duration before being reabsorbed. This is why virtual photons mediate forces over measurable distances. They live long enough to travel from one charged particle to another, transmitting the electromagnetic interaction. The force you feel when you push against a table is fundamentally due to virtual photons exchanged between electrons in your hand and electrons in the table's surface. Forces are borrowed energy in motion. The strong nuclear force, which binds quarks together inside protons and neutrons, operates through virtual gluons. The weak nuclear force, responsible for certain types of radioactive decay, uses virtual W and Z bosons, which are massive and therefore can only exist for extraordinarily brief intervals. The more massive the mediating particle, the shorter its range, because mass corresponds to energy, and high energy means short lifetime. The universe enforces its borrowing rules across all forces. But here's something peculiar. The vacuum doesn't just allow borrowing, it demands it. The uncertainty principle isn't optional. Fields must fluctuate. Energy cannot be perfectly defined at every moment. So the borrowing isn't a loophole, it's mandatory. A field sitting perfectly still, with zero energy and zero fluctuation, would violate quantum mechanics. The universe forbids that state. So the vacuum seethes with activity, particles and antiparticles constantly appearing and disappearing, energy sloshing around in patterns too rapid and too small to observe directly, but too persistent to ignore. Does this mean the vacuum contains infinite energy? Potentially. If you sum the energy contributions from all possible virtual particles at all possible frequencies, the result diverges. It becomes infinite, which is obviously unphysical. This is one of the deepest unsolved problems in theoretical physics, the cosmological constant problem. Why doesn't the vacuum energy we calculate match the vacuum energy we observe, which is vastly smaller? No one knows. There are proposals involving cancellations, symmetries that cause positive and negative contributions to almost perfectly offset each other, leaving a tiny residual energy that matches observations. But the required cancellation is so precise, so delicate, that it seems implausible without deeper principles we haven't discovered yet. So the debt itself remains mysterious. The borrowing happens. The repayment happens. But the total balance of the vacuum, what it fundamentally contains, is unknown. Still, the local borrowing, the short-term fluctuations, those are well understood. Virtual particles appear according to calculable probabilities. They exist for durations determined by how much energy they carry. They influence real particles in measurable ways. And then they vanish, energy returned, balance restored. The cycle repeats endlessly. And from this cycling, from this constant borrowing and repayment, much of what we call reality emerges. Forces, particle masses, the structure of atoms, the stability of matter. Even the fact that electrons don't spiral into atomic nuclei, which classical physics would predict, is partially due to virtual particles creating a kind of cushion around the nucleus, an effective repulsion that stabilizes the electron's orbit at quantum mechanically allowed energy levels. The vacuum participates in every interaction. Nothing happens in isolation from the fluctuating fields. And those fields never rest, never deplete, never exhaust their capacity to lend energy briefly before taking it back. It's as though the universe runs on credit, every particle and force drawing from a reserve that permits temporary overdrafts, as long as the accounts balance quickly enough. And they always do. The timing is built into the physics. You can't cheat the repayment, can't extend the loan beyond what uncertainty allows, can't borrow more than the vacuum will permit for a given duration. The rules are absolute. But within those rules, the vacuum is generous. It allows an endless stream of particles to flicker into existence, to briefly interact with the world, to leave traces in the form of shifted energy levels and altered forces, and then to disappear as if they were never there. Which, in a sense, they weren't. Virtual particles are potentialities made temporarily concrete, borrowing from the possible to influence the actual, then dissolving back into possibility. And this process underlies everything. Every force you've ever felt, every photon you've ever seen, every atom in your body. All shaped by particles that existed only long enough to deliver their influence and then vanish. The debt is paid. Always. But while it's borrowed, it changes things. Briefly. Enough. A single atom sits in isolation. Its electron occupies a superposition of energy levels, ground state and excited state simultaneously. The wave function describes both with clear amplitudes. Both components interfere. Now introduce a photon. The photon interacts with the atom. If the electron is in the ground state, the photon passes through unaffected. If the electron is excited, the photon scatters. After the interaction, the system contains correlations. One component of the wave function has the electron in the ground state and the photon traveling straight. Another component has the electron excited and the photon deflected. Both components exist. Both contribute to the total state. But now the electron's state depends on the photon's trajectory, and the photon's trajectory depends on the electron's energy. They're entangled. This is not collapse. The superposition hasn't reduced to one outcome. It's spread across two systems instead of one. The electron alone no longer has a definite state. Neither does the photon. Only the combined system has a well-defined wave function. And if the photon escapes into the environment, traveling far away, interacting with other particles, the correlation persists but becomes inaccessible. You can no longer measure both the electron and the photon together. The information about their relationship disperses. The electron appears to be in one state or the other, not because it chose, because you can't see the photon anymore. This is decoherence, not the collapse of possibilities into one reality. The dispersal of quantum information into the environment. The entanglement of a small system with a large, uncontrollable one. The loss of interference between different components of the wave function. It looks like collapse. Functions like collapse. But fundamentally differs from it. Collapse would mean the other possibilities cease existing. Decoherence means they exist but can't be accessed. The distinction matters. Start with something small, an electron in a magnetic field. Its spin points either up or down relative to the field direction. In superposition, it points both directions. The electron radiates. Photons carry away energy. Each photon's polarization becomes correlated with the spin direction. Spin up emits one polarization, spin down emits another. After many photons escape, the spin state appears definite when measured. But the superposition still exists in the combined state of electron plus environment. One term has spin up and photons polarized one way. Another term has spin down and photons polarized differently. Both terms persist in the wave function. They no longer interfere because the photons carry different information. Interference requires identical states in everything except the property being measured. If the photons differ, the states aren't identical. The interference terms in the density matrix vanish. This is decoherence, the suppression of quantum interference through environmental entanglement. Scale up. A molecule vibrates in a superposition of positions, here and there, a nanometer apart. Air molecules collide with it. Each collision transfers momentum. The trajectory of the air molecule depends on where the molecule was during impact. Different positions mean different scattering angles. After one collision, the molecule's position becomes entangled with one air molecule's momentum. After 1,000 collisions, entanglement spreads across 1,000 air molecules. After 1 billion, the original superposition is buried in correlations. You'd need to measure every air molecule that collided with the object to reconstruct the quantum state. Impossible. The air molecules thermalize. They collide with other molecules, spread the information further. Within microseconds, the correlation between the molecule's original position and the environment state becomes irretrievable. The superposition hasn't collapsed. It's dissolved into the environment. The molecule appears classical not because quantum mechanics stopped applying, but because the quantum information leaked out. Decoherence creates the appearance of definite position without requiring actual wave function collapse. Continue scaling. A grain of dust floats in air. Trillions of atoms. Each atom coupled to the electromagnetic field. Each interaction with thermal photons creates correlations. The dust grain emits infrared radiation constantly. Every photon carries information about the grain's temperature, position, internal configuration. The photons disperse into the surroundings, absorbed by walls, scattered by other particles, lost. The grain's wave function becomes entangled with quadrillions of environmental degrees of freedom. Tracking them all would require knowing the quantum state of the entire room. Every molecule, every photon, every vibrational mode. Thermodynamically impossible. So the grain decoheres completely, its quantum behavior suppressed, its position definite for all practical purposes. But in principle, the superposition remains. If you could reverse every interaction, undo every entanglement, trace back every photon and air molecule collision, you could restore the original quantum state, unscramble the information, recover the coherence. This is what unitarity guarantees. Quantum evolution is reversible. Information is never destroyed, only dispersed. But dispersal beyond retrieval is functionally equivalent to destruction. And this is the heart of decoherence. It doesn't solve the measurement problem completely. It doesn't explain why you observe one outcome instead of experiencing the superposition. It doesn't tell you which branch of the wave function corresponds to your subjective experience. What it does is explain why macroscopic superpositions don't persist, why cats aren't observed to be both alive and dead, why measurement devices show definite readings. Because the environment measures everything constantly. Every macroscopic object is monitored by its surroundings. Photons, air molecules, thermal vibrations, gravitational interactions. These interactions entangle the object's quantum state with the environment faster than any experiment can isolate it. Decoherence times for everyday objects are astonishingly short. Nanoseconds, picoseconds, shorter than anything measurable. So the classical world emerges, not from new physics, not from wavefunction collapse, from the uncontrollable complexity of the environment. Could you prevent it? To some extent. Quantum computers operate by minimizing decoherence. They cool systems to millikelvins, shield them from electromagnetic radiation, isolate them from vibrations, operate in vacuum chambers. These measures extend coherence times, milliseconds instead of nanoseconds, enough to perform calculations, but never indefinitely. Even in the best isolation, stray cosmic rays penetrate the shielding. Virtual particles fluctuate in the vacuum. The gravitational field couples to mass energy distributions. Decoherence creeps in. Perfect isolation is impossible. The universe is interconnected. Every quantum system touches the larger world. Fields extend everywhere. Photons propagate through space. Gravity couples to all energy. So decoherence is inevitable. The question is only how fast. And the answer depends on how strongly the system couples to the environment. A well-isolated ion in a trap decoheres slowly. A dust grain in air decoheres rapidly. A human body, radiating heat, breathing, moving, decoheres essentially instantaneously on quantum timescales. This is why you never observe yourself in superposition. Your neurons fire or don't fire. Binary states encoded in chemical and electrical signals. But each state involves the motion of countless molecules, the emission of thermal photons, the interaction with surrounding tissues. The environment entangles with your brain state continuously. Decoherence happens faster than neuronal dynamics, faster than thought. So consciousness experiences definiteness. Not because collapse occurred, because the quantum information about your brain state leaked into the environment before awareness could track it. The superposition dispersed, blurred beyond recognition. Like a sound in a canyon. The original note travels outward, reflects off walls. Each reflection creates echoes. Echoes overlap, interfere. Eventually, the echoes become noise. The original note is still there, encoded in the complex pattern of reverberations, but reconstructing it from the noise requires knowing every surface, every reflection, every interference. Practically impossible. Decoherence is like that. The original superposition scatters into the environment, becomes encoded in an impossibly complex pattern of correlations. Technically reversible, practically irretrievable. And once irretrievable, it might as well be gone. This is why decoherence explains the emergence of classicality. It shows how quantum mechanics, without modification, produces a world that appears classical. Not through collapse, but through dispersal, through the hiding of quantum information in environmental complexity. The quantum world doesn't vanish. It just gets tangled. With everything. Everywhere. Until tracking it exceeds all possible resources. And then, for all practical purposes, it's classical. Even though fundamentally, it remains quantum. Hidden. Dispersed. Entangled with the entirety of its surroundings. Still there. But blurred beyond seeing. Hold your hand in front of you. It doesn't shimmer. Doesn't split into multiple positions. Doesn't tunnel through solid objects or interfere with itself. Your hand is classical. But it's made of atoms. And atoms are quantum. Each electron exists in superposition until measured. Each nucleus occupies a wave function, not a point. So where does the quantum behavior end and the classical begin? Nowhere specific. There's no threshold, no particle count that marks the boundary, no size or mass or temperature where physics switches from one set of rules to another. Quantum mechanics applies to everything, always. What changes is observability. Small systems maintain coherence long enough to measure quantum effects. Large systems decohere too quickly. The transition isn't in the physics, it's in what survives interaction with the environment. Consider mass. A single atom exhibits clear quantum behavior, superposition, interference, tunneling. Two atoms bonded together can do the same. So can a molecule with 10 atoms, 100. Under the right conditions, thousands. In 2019, researchers demonstrated interference with molecules containing over 2,000 atoms. Each molecule passed through both slits simultaneously, created a pattern. That's already macroscopic on molecular scales. But decoherence limited the experiment. The molecules had to be cooled, shielded from air, isolated from stray photons. The interference fringes appeared only under extreme care. Add more mass and decoherence accelerates. A grain of dust weighs billions of times more than those molecules. Its surface area is vast. Thermal photons radiate from it constantly. Air molecules bombard it. The dust grain decoheres in less than a picosecond, far faster than any measurement apparatus can operate. You can't observe its superposition because the environment collapses it before you can look. So, mass matters. But not absolutely. A sufficiently isolated massive object could maintain superposition. In principle. The real barrier is isolation. Temperature plays a role too. Warm objects radiate. Each photon carries information about the object's state. Each photon that escapes entangles the object with the environment. Cool the object and radiation decreases. Fewer photons. Slower decoherence. Longer coherence times. But even at absolute zero, which is unreachable, quantum field fluctuations persist. The vacuum never stops interacting. Gravity couples to mass regardless of temperature. So temperature extends the boundary, but doesn't eliminate it. The shift from quantum to classical depends on context. What are you measuring? A molecule's position or its internal vibrational state? Position decoheres quickly because it couples strongly to the environment. Vibrational states can remain coherent longer because they're more isolated. The same object can behave quantum mechanically in one property and classically in another. Simultaneously. A protein in a cell vibrates quantum mechanically. Its atoms occupy superpositions of vibrational modes. But its position in the cell is classical, definite, localized. The boundary isn't in the object. It's in the observable. Some properties couple strongly to the environment, others weakly. Strong coupling means fast decoherence. Weak coupling allows quantum behavior to persist. This is why superconductors can exhibit macroscopic quantum effects. Electrons pair together at low temperatures. The pairs form a collective state that spans the entire material. Currents flow without resistance. The current can be in superposition, clockwise and counterclockwise simultaneously. This is macroscopic, measurable. Millions of electrons moving together in a quantum state. But it requires isolation, cooling, shielding from magnetic fields. The moment warmth enters or a stray field penetrates, decoherence sets in. The superposition fades. So the classical world is conditional, not inevitable. just probable under most circumstances. The circumstances we inhabit: room temperature, atmospheric pressure, surrounded by thermal radiation, bathed in electromagnetic noise, constantly coupled to the environment. Under these conditions, quantum behavior vanishes rapidly for anything larger than molecules. But change the conditions and the boundary shifts. Cool to millikelvins, isolate in vacuum, shield from fields. Suddenly, macroscopic quantum states become accessible. The boundary isn't fixed. It's negotiable. And even in everyday conditions, quantum effects persist in hidden ways. Chemistry is quantum. The bonds holding molecules together. The reactions that power cells. The structure of proteins. Electrons in those bonds exist in superpositions of orbitals. They tunnel through energy barriers. They interfere with themselves. But the molecules themselves appear classical, localized, definite, quantum at small scales, classical at large scales, both happening in the same system. This layering is universal. Your body is classical in its motion. You don't tunnel through walls. Your position is definite. Your mass obeys Newton's laws. But the enzymes in your cells catalyze reactions through quantum tunneling. Electrons jump energy barriers they couldn't classically cross. Protons tunnel between molecules. Quantum mechanics enables the chemistry that keeps you alive. But decoherence keeps your body from exhibiting quantum behavior as a whole. The boundary runs through you. Through everything. It's not a line. It's a gradient. A transition region where quantum effects fade into classical behavior. Smooth. Continuous. And it moves. Depending on what you're looking at. Depending on how carefully you isolate. Depending on timescales. A superposition that lasts nanoseconds is classical for all practical purposes if your measurement takes milliseconds. But if you can measure in picoseconds, quantum behavior appears. The boundary depends on the observer's capabilities. Not consciousness. Technology. Precision. Speed. Better tools reveal quantum behavior in larger systems. Worse tools see only classical outcomes. So the question, where does classical begin, has no single answer. It begins wherever decoherence becomes faster than measurement. For a dust grain in air, that's immediate. For an ion in a trap, it's seconds. For a superconducting loop, minutes. The physics doesn't change across these examples. The environment does. And the environment determines what survives. Quantum coherence, or classical definiteness. Both descriptions are accurate, just at different scales. Different timescales. Different levels of isolation. The universe doesn't draw a line. We do. Based on what we can measure. Based on what persists long enough to observe. And that line shifts. As technology improves, as isolation techniques advance, the boundary between quantum and classical moves toward larger systems, heavier masses, longer timescales. Eventually, we may observe superpositions in objects visible to the naked eye, or we may find fundamental limits, limits imposed by gravity, limits from space-time structure, limits we haven't yet discovered. But so far, no such limit has appeared. Every time isolation improves, larger systems exhibit quantum behavior. The boundary recedes, suggesting it's not fundamental, just practical, a consequence of decoherence, of environmental coupling, of the difficulty of maintaining isolation, not a law of nature, just a fact about our universe. That it's filled with fields, radiation, particles, interactions, and those interactions blur quantum behavior into classical outcomes, gradually, without ever fully eliminating the quantum substrate beneath. So classical begins nowhere, and everywhere, depending on where you look and how closely. You've sent the last particle through, and the detector has recorded its position. And now you're looking at the screen where thousands of impacts have accumulated into a pattern that shouldn't exist if particles travelled like bullets, but does exist because they don't. Bright bands alternating with dark regions, stripes of high and low density that stretch across the detection area. And this pattern tells you something happened that classical physics cannot explain, that each particle somehow knew about both openings, even though it passed through as a single localized event. The experiment is over, but the questions remain, sitting there in the pattern itself, in the gaps where no particles arrived, even though both slits were open, and geometry alone would predict uniform scattering. And you're left with the fact that something about the two paths interfered, cancelled in certain locations, reinforced in others. And now you want to know which slit each particle used, so you place detectors at the openings, small devices that register when a particle passes through, nothing invasive, just a gentle measurement of presence. And you run the experiment again, expecting to see the same interference pattern, plus the additional knowledge of which path was taken. But the pattern vanishes. The screen now shows two broad distributions, one centered behind each slit, exactly what you'd expect if particles were classical objects that traveled through one opening or the other. And the interference is gone completely, not reduced but absent, as if the act of knowing which path was taken erased the quantum behavior that created the original pattern. You didn't block the slits, didn't add barriers, didn't change the geometry or the particle energy, or anything about the physical setup, except for the presence of detectors that recorded which slit was used. And that alone was sufficient to destroy the interference. This is the cost of knowing. When path information exists anywhere in the system, when the universe contains a record of which route the particle took, the different paths no longer interfere, because interference requires indistinguishability, requires that the two routes remain quantum mechanically identical in every aspect except the property you're trying to measure. And the detectors introduced a difference, a correlation between path and detector state that breaks the symmetry. It's not that the detectors physically disturbed the particles in a way that scrambled their trajectories, though early interpretations suggested this, but rather that the detectors became entangled with the path information, creating separate branches of the wavefunction for left slit plus detector clicked and right slit plus detector silent, and these branches no longer share the phase relationship necessary for interference. You can verify this by erasing the path information after the particle is passed through, but before it reaches the screen, using a clever arrangement where the detector records are destroyed or randomized in a way that makes it impossible to determine which slit was used. And when you do this, the interference pattern returns, restored not because the particle changed its behavior retroactively, but because the system no longer contains the information that would distinguish the paths. Knowing prevents interference, and not knowing allows it, and the transition between these states is sharp, binary, determined entirely by whether path information exists in a recoverable form anywhere in the experimental setup. This raises an uncomfortable question about what it means to measure, about whether the detectors need to be read by a conscious observer, or whether their mere presence, their physical interaction with the particle, is sufficient to count as measurement. And experiments have shown that consciousness plays no role, that unread detectors destroy interference just as effectively as read ones, that the information need only exist, not be known. So the in principle be determined from the state of a system, and this caring manifests as the suppression of interference whenever distinguishability enters, whenever the different paths leave different marks on the world. and you start to wonder what this means for the particle's journey, whether it really travelled both paths when no detectors were present, or whether it always took one route and the interference pattern emerged from some other mechanism, some deeper structure of reality that mimics the behaviour of particles taking multiple paths without requiring them to actually do so. But the mathematics is clear. The wave function genuinely splits at the barrier and propagates through both openings, carrying definite amplitude and phase for each route. And when these two components of the wave function recombine at the screen, they add together according to the rules of quantum superposition, constructively where their phases align and destructively where they oppose. And this produces the observed pattern with precision that matches experiment perfectly. So the particle does take both paths in the sense that its wave function, the mathematical object that describes its quantum state, contains terms corresponding to both routes. And these terms are equally real, equally part of the physical description, not mere possibilities, but actual components of the state that contribute to measurable outcomes. Until measurement. Until something in the environment becomes correlated with which path was taken, and then the two components decohere, stop interfering, begin to behave like separate classical possibilities of which only one can be real, and the system transitions from a superposition that encompasses both paths to a mixture that represents one path or the other with specific probabilities. And what you're left with, sitting there after the experiment has finished and the data has been collected and the detectors have been read, is the knowledge of which slit each particle used and the absence of the interference pattern. A trade where information about the path replaced the quantum behaviour that would have occurred without that information. And you can't have both. This is complementarity, the principle that certain pairs of properties cannot be simultaneously known with arbitrary precision, not because of technical limitations, but because the quantum state of a system cannot contain definite values for both at the same time, and path information versus interference visibility is one such pair, where increasing knowledge of which path was taken necessarily decreases the contrast of the interference pattern until, at complete path knowledge, the pattern disappears entirely. Some experiments demonstrate partial knowledge, where the detectors provide imperfect information about which slit was used. Maybe they fail to register 20% of the time, or their signals are noisy. And in these cases you see a reduced interference pattern, stripes that are still visible, but with lower contrast, as if the system is partially quantum and partially classical, depending on how much distinguishability has been introduced. And this makes sense within the framework of decoherence, where the degree of entanglement between the system and the environment determines how much interference survives, with weak coupling preserving most of the pattern and strong coupling erasing it, and the detectors at the slits are just another source of coupling, another channel through which path information can leak into the environment. So the double slit isn't really about particles or waves, isn't about whether light or electrons are fundamentally one thing or another, but about the relationship between knowledge and quantum behaviour, about how the presence of information in the world affects what kinds of patterns can emerge. And when you sit with this, when you let the implications settle, it starts to feel less like particles are doing something strange, and more like reality itself has a structure, where certain combinations of knowledge are forbidden, where asking one question necessarily obscures the answer to another, where the universe enforces a kind of informational economy that prevents complete knowledge of all aspects of a system simultaneously. It's like trying to see both sides of a coin at once, not because your eyes aren't good enough, but because the geometry of three-dimensional space doesn't permit it, because position and perspective are linked in a way that makes certain views mutually exclusive. And quantum mechanics does something similar, but with knowledge itself, with the information content of physical states. Lose the interference. Preserve the interference, lose the path. And this isn't a limitation of technology or measurement precision, but a feature of how quantum information works, how it's distributed across a system, how entanglement and superposition structure the possibilities in ways that classical thinking doesn't accommodate. And the double slit makes this visible, makes it concrete, turns an abstract principle into stripes on a screen that either appear or don't, depending on what else you chose to know. The experiment sits there in its completed state, the data recorded, the particles long since absorbed by the detection screen, and what remains is the pattern, or the absence of it, the result that tells you whether path information existed during the particle's transit. And you can look at that result and know immediately whether someone placed detectors at the slits, even without checking, because the pattern itself encodes that information, carries the signature of whether distinguishability was present. And in a way, this is the strangest part, that the outcome of an experiment depends not just on the physical configuration, but on the informational configuration, on what could in principle be known about the system's history. And this dependence is absolute, unambiguous, reproducible across millions of trials. Which means information isn't just something we track or record, isn't just a human concept imposed on nature, but is woven into the fabric of quantum mechanics itself, is part of what determines how systems evolve and what patterns emerge. And the double slit is maybe the clearest demonstration of this, because it shows that knowing changes outcomes in ways that have nothing to do with physical disturbance. The detectors don't need to touch the particles roughly, don't need to impart momentum or energy. They just need to record, to create a correlation, to establish that this detector state corresponds to this path. And that's enough. That correlation alone is sufficient to erase the interference and transform quantum behavior into classical probability. And sitting with that, sitting with the finished experiment and the pattern it produced or didn't produce, you're left with a kind of quiet certainty that something fundamental about reality is being revealed here. Something about the limits of what can be simultaneously true, about how the act of establishing one kind of knowledge necessarily forecloses another. Not because we're clumsy, or because our instruments are crude, but because that's how quantum states work, how they structure information, how they partition reality into complementary aspects that cannot coexist in definite form. And the double slit is the simplest, most direct way to see this, to watch it happen, to hold in your hands the evidence that knowing costs something, that information and interference are traded against each other in a balance the universe maintains without exception. And the particles are at rest now, absorbed, their journeys complete. And what you have is the record, the pattern they left behind. And that pattern is an answer to a question you didn't need to speak aloud. Did you watch which path they took? The screen already knows. An electron orbits a nucleus. It doesn't trace a path. Classical orbits don't exist at quantum scales. The electron occupies an orbital. An orbital is a region, a cloud of probability. The electron exists throughout the entire cloud simultaneously, not because it's moving too fast to track, not because measurement precision is limited, because the electron genuinely has no single position until position is measured. This is superposition, not uncertainty, not indecision. The electron isn't somewhere specific that we simply don't know. It's distributed across the orbital, present in all regions with varying probability density. Before measurement, asking, "Where is the electron?" has no answer. The question assumes a property that doesn't exist yet. Position becomes real when measured, not revealed, created. The wavefunction describes the electron's state completely. It contains all knowable information. And for an electron in an orbital, that information doesn't include a definite location, just probabilities. This seems strange because macroscopic objects always have positions. Your hand is in one place, not distributed, not smeared across space. But your hand is made of electrons. And those electrons individually occupy superpositions. Multiple energy levels at once before measurement. Multiple positions. Multiple momenta. The aggregate behaves classically because decoherence forces it. Environmental interactions constantly measure the electrons. Position information leaks into air molecules, photons, thermal vibrations. Superposition collapses continuously. But the underlying reality remains quantum. Superposition is the default. Definiteness is what requires explanation. Why do we expect otherwise? Because evolution shaped perception for survival, not accuracy. Organisms that treated predators as being in definite locations survived. Those that perceived predators as probability clouds did not. Natural selection favored classical thinking. But thinking classically doesn't make reality classical. It just hides the quantum substrate beneath experience. Consider a photon traveling through space. Its polarization can be vertical or horizontal, or diagonal, or circular. These aren't different photons. They're different bases for describing the same quantum state. A vertically polarized photon is a superposition of left and right circular polarizations. A diagonally polarized photon is a superposition of vertical and horizontal. The photon exists in all descriptions simultaneously. Measurement chooses a basis, forces the photon into one component of whichever superposition you're measuring. But before measurement, all components coexist. Not as possibilities, as actualities. The photon is vertically polarized and horizontally polarized, and everything in between, all at once, with amplitudes that determine how likely each outcome is when you finally measure. And this applies to every property. Spin, energy, momentum, position. A particle in free space has no definite momentum. Its wave function spreads across all possible momenta. Some values have higher amplitude than others, but they all exist. Measure momentum and you get one value. But you didn't find it. You created it. This isn't philosophy. It's testable. Prepare identical particles in the same quantum state. Measure momentum on half of them. Measure position on the other half. The momentum measurements scatter across a range. The position measurements scatter too. And the product of their spreads obeys Heisenberg's uncertainty principle. Not because measurements disturb the particles, because the particles genuinely had neither definite momentum nor definite position before measurement. They existed in superpositions of both. And those superpositions are real. Not incomplete knowledge, not hidden variables waiting to be discovered. Real quantum states where multiple values coexist. What does coexistence mean? Physically, it means the wave function, the mathematical object describing the particle, contains terms for each value. Each term contributes to observables. Each term affects how the particle behaves in interactions, in interference, in entanglement. Remove one term, and predictions change. This has been tested. You can prepare a particle in a known superposition, manipulate it, then verify that all components were present during manipulation by observing interference effects that only occur if both existed. Superposition isn't epistemic. It's ontic. The particle doesn't have a hidden value you're ignorant of. It has multiple values. Literally. Simultaneously. This violates intuition. Macroscopic objects aren't in multiple states. A coin on a table is heads or tails, not both. But microscopically, the atoms in the coin are in superpositions. Their electrons don't have definite positions. The nuclei don't have definite momenta. So why does the coin look definite? Decoherence. Again, the coin interacts with air, light, the table surface. These interactions entangle the coin's state with the environment. Different macroscopic configurations, heads versus tails, coupled to vastly different environmental states. Air molecules scatter differently depending on which face is up. Photons reflect differently. Pressure distributions change. The environment measures the coin constantly, and those measurements decohere the superposition faster than anything observable. By the time you look, the coin is in one state, has been for nanoseconds already. But technically, the superposition persists. Buried in correlations with the environment, if you could reverse every air molecule collision, every photon reflection, every thermal fluctuation, you'd recover the superposition. Prove both states were there. Impossible practically, possible in principle. So the coin is in superposition, just not observably. And this suggests something unsettling. Maybe everything is always in superposition. Every particle, every atom, every object. And definiteness is just decoherence. Local, temporary, imposed by environmental entanglement. In this view, the classical world is a facade, a high-level description that emerges when quantum information becomes inaccessible. Underneath, superposition never ends. The universe is in superposition of all possible configurations. We experience one branch, but the others exist. Equally real, equally definite within their own contexts. This is one interpretation, not provable, not disprovable, but consistent with the mathematics. Another view says superposition genuinely collapses. One outcome becomes real, others cease existing. But even in collapse interpretations, superposition is real before collapse. The particle exists in multiple states. Then measurement happens. One state survives. Either way, superposition is physical, not abstract, not conceptual. Particles really are in multiple states before measurement, and this is normal. Superposition is the default mode of quantum systems. Isolated particles naturally evolve into superpositions. Energy eigenstates superpose. Position states spread. Momentum distributions broaden. Keeping a particle in one definite state requires constant measurement, constant interaction, constant environmental coupling. Definiteness is what requires effort. In deep space, far from any matter or radiation, a particle would drift into deeper and deeper superpositions, position spreading over light years, momentum approaching perfect uncertainty. No decoherence, no collapse. Just expanding superposition. Forever. And the particle wouldn't be confused, wouldn't be deciding, just existing in the only way quantum mechanics allows. Multiple states. Simultaneously. The strangeness isn't in the particle, it's in us, in our expectation that things must be one way at a time, that properties must have single values, that reality must be definite. But quantum mechanics says otherwise. Properties can have multiple values. Particles can occupy multiple states. Reality can be indefinite. And this is normal. Certainty is the exception. Superposition is the rule. We live in the exception, the narrow regime where decoherence forces definiteness. But beneath that, always, superposition remains. There are questions you cannot answer. Not because the instruments aren't sensitive enough, not because the theory is incomplete, not because someone hasn't tried hard enough, but because the structure of quantum mechanics forbids certain combinations of knowledge from existing simultaneously. The universe has built-in limitations, hard boundaries. These are the uncertainty relations. Heisenberg discovered the first one in 1927, the relationship between position and momentum that states you cannot know both with arbitrary precision, that improving your knowledge of where a particle is necessarily degrades your knowledge of how fast it's moving and in which direction. This isn't a statement about measurement disturbance. It's deeper. A particle with perfectly defined position has completely undefined momentum. Every possible momentum value exists in the wave function with equal amplitude. Conversely, a particle with perfectly defined momentum has completely undefined position. Its wave function spread uniformly across all of space, no location more probable than any other. These are limiting cases. Some position uncertainty, some momentum uncertainty. The product of these uncertainties must exceed a minimum value. That minimum is Planck's constant divided by 2, a number so small it's irrelevant at human scales, but dominant at atomic scales, and it represents an absolute floor beneath which uncertainty cannot be compressed, no matter what techniques you employ. Squeeze position uncertainty down, and momentum uncertainty expands. Always. This pairing repeats across physics. Energy and time form another pair, where measuring energy with high precision requires long observation times, and measuring an event's timing with high precision necessarily leaves energy uncertain. Angular momentum components obey similar relations. Knowing one component perfectly makes the others completely indefinite. These aren't failures of technology. They're properties of reality. The uncertainty relations arise from the wave nature of quantum states, from the fact that wave functions are mathematical objects called wave packets that have intrinsic width in conjugate variables, and you can make a wave packet narrow in position only by combining many different momentum components, which means the momentum becomes spread out. Or you can make it narrow in momentum by combining many different positions, which spreads the position. It's reciprocal. Like the relationship between musical pitch and duration. A note held for a long time has a well-defined frequency. You can identify the pitch precisely. But a note played very briefly, just a short click, has frequency components spread across a wide range. The pitch becomes ambiguous. You cannot have both a perfectly precise pitch and a perfectly short duration, because these properties are Fourier transforms of each other, mathematically conjugate, and this relationship exists independently of how you measure them, independently of your instruments, independently of consciousness. It's geometry, structure. Quantum mechanics inherits this structure. Position and momentum are Fourier transforms of each other in the wave function representation, so their uncertainties follow the same reciprocal relationship that pitch and duration follow. And this means the uncertainty isn't about ignorance or disturbance, but about the fundamental mathematical structure of how quantum states are described. You can't compress both simultaneously. Ever. The universe enforces this. Not through active prevention, not through some mechanism that stops you when you try to measure too precisely, but through the passive fact that quantum states simply don't contain the information you're asking for when you try to specify both conjugate variables exactly. The state of maximum position precision has zero momentum precision. Not because something is hidden, because momentum genuinely doesn't have a value. This is hard to accept. Classical intuition says objects have positions and momenta, definite values, simultaneously real. And at macroscopic scales, this seems true because the uncertainties are so tiny compared to the quantities being measured that they vanish into noise, and a baseball travelling through air has position uncertainty measured in fractions of atomic diameters, and momentum uncertainty far smaller than any measurement could detect. So for all practical purposes, both are definite. But they're not. Fundamentally, even the baseball has uncertainty, just undetectable. For electrons in atoms, the uncertainties dominate, determining orbital sizes, energy levels, the entire structure of chemistry, and thus biology, and thus everything constructed from matter. The uncertainty principle is why atoms have volume, why electrons don't collapse into the nucleus, why matter is stable. If electrons could have both zero position uncertainty and zero momentum uncertainty, they would spiral into the nucleus and atoms would collapse. But the uncertainty principle prevents this by ensuring that confining an electron to a small region near the nucleus necessarily gives it large momentum uncertainty, which translates to kinetic energy, which creates an effective repulsion that balances the electromagnetic attraction. Stability emerges from uncertainty. So the limits aren't obstacles, they're structure. They shape what exists. And they're permanent. No future technology will violate the uncertainty relations because they're not technological limits, they're mathematical properties of how information can be distributed across quantum states, and unless the fundamental structure of quantum mechanics is wrong, which seems unlikely given its success, the uncertainties will remain. Forever. Some things stay unknown. Not unknowable in the sense that they exist but are hidden, but unknowable in the sense that they don't exist until measured, and even then only one half of the conjugate pair can exist at a time, and asking for both is like asking for a wave to have a single frequency and a single instant of time, which is geometrically impossible. The universe contains permanent ambiguity. Built in. Irreducible. And this ambiguity underlies everything that happens, every particle interaction, every field fluctuation, every quantum event, because the uncertainties determine what configurations are accessible, what energies are allowed, what transitions can occur. They're not side effects, they're primary. Virtual particles exist because energy-time uncertainty allows it. Quantum tunneling occurs because position-momentum uncertainty creates probability tails. Atomic spectra have their observed patterns because uncertainty constrains the possible states. The limits enable. And they persist even at the boundary between quantum and classical, even in the regime where decoherence makes things appear definite, because decoherence doesn't eliminate uncertainty, it just hides it in correlations with the environment. The particle still has both position and momentum uncertainties. They're just entangled with environmental degrees of freedom now. Still there. Still real. You can't escape them. Cooling doesn't help because uncertainty exists even at absolute zero, manifesting as zero-point motion, the residual jitter that particles retain in their lowest energy state, because sitting perfectly still would violate the uncertainty principle. Isolation doesn't help because the uncertainty is intrinsic to the particle, not caused by external interactions. Better measurements don't help because measurement reveals uncertainty rather than reducing it. The universe is fundamentally fuzzy. At the smallest scales, at the quantum boundary, position blurs into a range, momentum spreads across values, energy fluctuates within bounds determined by duration, and nothing is perfectly sharp, perfectly defined, perfectly certain. And this fuzziness is what allows the quantum world to be quantum. Remove the uncertainty, and you remove superposition. Remove superposition, and you remove interference. Remove interference, and quantum mechanics collapses into classical mechanics. But that doesn't happen. The uncertainty remains, even where quantum behavior seems to fade, even where classical descriptions work. Because the classical world is an approximation, a limit where uncertainties become negligible compared to measured quantities, but never actually reach zero. Underneath, always, the quantum fuzziness persists. And so there are questions you will never answer. Where exactly is the electron and how fast is it moving? Unanswerable. When precisely did the decay occur, and what was the exact energy released? Unanswerable. What are the simultaneous values of all three components of angular momentum? Unanswerable. Not because of ignorance, because the questions assume a reality that doesn't exist. And this is where the boundary between quantum and classical becomes most clear, not in size or temperature or isolation, but in the nature of the questions you can ask. Because classical physics assumes all properties have definite values simultaneously, assumes you can, in principle, know everything about a system, And quantum mechanics says no. Some combinations of properties are mutually exclusive. Some knowledge is forbidden. The universe keeps secrets. Necessarily. Not out of caprice. Out of structure. And those secrets are what make reality quantum, what distinguish the actual universe from the clockwork deterministic universe classical physics imagined. And they're fundamental, woven into the mathematics, into the geometry of state space, into the fabric of how information works at the smallest scales. They're not going away. And maybe that's fitting, that even at the boundary, where quantum meets classical, where the strange becomes familiar, there remain things that resist knowing, quantities that refuse definition, questions that have no answers, not because we haven't found them yet, but because the answers don't exist. Uncertainty endures. At every scale, in every system, forever. And the world built on that uncertainty works. Atoms hold together. Chemistry proceeds. Stars burn. Life emerges. All resting on foundations that are irreducibly uncertain. Not despite the limits, because of them. The uncertainty is the structure. And at the boundary between quantum and classical, where particles become objects and waves become particles, and superposition becomes definiteness, the uncertainty remains. Quieter. Hidden. But present. Always. Thank you for listening to The Sleepy Physicist. If this helped you find some rest tonight, or gave you something to think about as you drift, consider subscribing to the channel so you can find more of these explorations. And if you feel moved to, a like helps others discover this space too. Sleep well, and rest in the uncertainty.